until now it was all kind of preparatory, so unfortunately we'll be moving to kind of slightly more complicated things, little by little. So, but there are these notes, like, so this talk I wrote, so there are 20 pages of notes. I mean, I really recommend reading it, because you can regard the lecture as some kind of, well, verbal explanations of what's written in the notes. All right, so the affine Grassmannian, so the Hecke action. So this talk might not have a punchline, so I'll basically explain a bunch of constructions. So in the end you might be bewildered. It's like, so what? So, and indeed it will be justified. So all right, so we start with the affine Grassmannian at one fixed point of the curve. So it's this guy. And so our interest today is the category that is denoted spherical of G. It's d modules of the affine Grassmannian, equivariant with respect to, so equivariant in the sense that Sam was talking about in his previous lecture. So this is acted on the left by G of OX. And I'll actually remind who G of X is. So we have.
With the exception that Sam did not mention interdimensional.
Don't spoil my game. So this is acting on this. Therefore, so he explained that the d modules on the geometric object is a category acted on by the group, and then we can pass to the equivariant category. And indeed, so what Sam did not talk about is that, so he only talked about kind of finite dimensional algebraic groups, and this one is not finite dimensional. Well, by the way, this is, well, at least this is a pre-stack of finite type. At least this guy is allowable from our point of view. So
Who is the pre-stack of finite?
the affine Grassmannian, it is of finite type. Finite type, but you know it is a finite type. Well, locally finite type. It's okay. So the goal now is to define on this a structure of monoidal category. And again, so you still must be on your guard because this object is ill-defined. So now I'll do something even worse, and then I'll comment. We'll define on this category a monoidal structure.
You said that something was what was ill-defined?
Well, we don't, so even if you accept completely what Sam said in his previous talk, so we only know what the equivariant category is when something finite dimensional is acting, and this is not finite dimensional. So far it's illegit.
This is a kind of naive definition.
Wait a second, let me proceed. So monoidal structure. So I'll give it to you by a formula. Well, I write the formula like this. So in fact, I'll be even more brutal, and I'll say it's d mods on G of Kx, equivariant with respect to two copies of G of X. One is acting on the left and one is acting on the right. And now you must be really on your guard, because this is, even if the affine Grassmannian was okay, this guy is definitely not okay. This is not a finite type, not locally finite type in any sense. So we have some infinite dimensional something acting on something different dimension, infinite dimensional something else, and what is this? Okay. Disregard that for a minute, and let me make an argument why it's really handy, and then we'll come back to it. So using this notation, if you wish, I'll define this braided monoidal structure, not braided, monoidal structure, as follows. Well, you consider the following thing. More of these infinite dimensional gadgets. So when I write this above the cross, it means that I'm dividing by the diagonal action. Yeah. So, and again, notation. D modules on some Satake quotient is the same thing by definition as the equivariant category on the original thing with respect to the group indicated. So we have the following diagram.
Can I ask an annoying question?
You know.
Those is defined in weeks.
Oh, pardon me?
You said something is true by definition, that D modules on Satake quotient are by definition equivariant D modules. The definition of what?
So the no. So we don't know what these kind of Satake quotients are. So these Satake quotients are not allowed, so we cannot just simply write D mods.
And again, they're not allowed because of what?
Infinite, not finite, not finite type, not locally finite.
Those D modules are not defined.
Yeah, so but still it's not expressed in the sense.
Just a sec, let me just answer one by
When
one.
you say that they're not allowed, what does it mean?
Well,
We don't have a definition of D
we set up the theory of D modules by this right-Kahn extension, starting from schemes of finite type. So far, we can only talk about D modules on pre-stacks that are called locally of finite type. So we just don't have this notion for the moment. But I'll keep pretending that we have this notion. Yes, Sergey. Okay. Yes.
What goes wrong if it states the Theorem space?
Pardon me?
What goes wrong if it states Q cough and the Theorem space?
The Theorem space is nonsensical. Like, I mean, it's kind of completely unwieldy. So there is this map from here. So it's a product of the same two similar things. So to map to this factor, well, you just use this factor. You divide out by this action here, and here similarly here, and then it has a multiplication map and so what you want to do, you want to pull, push. And that will be a monoidal operation. Okay, so we have to make sense of these things. So I don't believe in D modules that you can give an intrinsic definition of D modules not in finite type. So what I'll do during the tutorial after this talk, I will explain how to give the definitions to all these gadgets, basically extrapolating from finite type. So I'll explain the algorithm, how the theory of D modules for pre-stacks in finite type gives rise to kind of a reasonable theory here, so that these operations are allowed. So it's the kind of map with respect to which you can't take pull back, and this is the kind of map with respect to which you can take push forward. So for now, for lack of other choice.
It's a new approach compared to what people were doing.
No, it's meaning what?
Well, I mean, just using the fact that for unipotent group,
No.
nothing changes.
Well, that will definitely be taken into account. No, what I'll say will be nothing fancy. I will not say anything kind of, no inventions here. You have to just carefully say what I mean by D modules in not in finite type, and set up the functorialities. I'll basically go back to Victor's old paper. Where is Victor? Not here. All right. So now let's talk about the geometric Satake. So first of all, this category, well, whatever it is, it has a forgetful functor that's denoted by oblivion to just D modules on the affine Grassmannian. And so the claim is that this category has a unique T structure for which this functor is T exact. Sf. And so it's a basic theorem, and I'm forgetting.
This is also somehow you take sort of D modules in the naive sense and then make it a complete category.
Yes.
So the compact objects are just D modules supported to five dimensions.
Yes. And
Can I ask?
yes.
So from this you define
The what? I what?
From this you define a monoidal structure on the D module of this, yes?
So here it was defined on Sf. There is there's a monoidal structure.
Yeah, but from this action you
So this diagram is meant to explain that this category has a monoidal structure.
So I'm asking if it's commutative.
It's not.
Geometric?
Well, it's a good question. We'll get there. Yes and no, in a very precise sense. Okay, so now there's a basic theorem, and I'm forgetting who the proper attribution goes to, probably Lustig, that says that so the monoidal operation preserves the heart. So therefore, this heart becomes an abelian category with a monoidal structure. All right, and now comes the geometric Satake, which I'm assuming that people have seen before. So, namely, theorem, so it is Ginsburg and Mirkovic-Villanen, that says the following, that so there is a canonical equivalence denoted Satake. We call it Satake heart. We consider the category of representations of the Langlands dual group. Take its heart, and it goes to Sf heart. So, and by the way, it's day 3 of the conference, and this is the first time when we see the relationship between G and G check. That's how it appears. So before the two sides were completely separate, and now it's the first time that we have G and G check simultaneously on the board. Okay, so this is the basic theorem.
This little bird means that
Heart. Backslash heart. Backslash heart suit.
this is about the billion.
To me, it looks like a devil's head.
But there is no appropriate tech command. All right. So, okay. So now,
What do you mean by heart? What is the T structure? Does it talk about?
so I said that it has a unique T structure for which this functor oblivion is T exact. And then I said that there's a theorem that this T structure, the heart, is preserved by the monoidal operation. Okay, now, so what I want to do, I want to use this theorem to construct a functor that I'll call Satake. It's Satake at a point. I'll call it Satake naive, that will go from the entire rep G check, I mean the DG category, to Sf. So there is a general theorem involved, and it's in this form. It's proved by Lurie, and it says like this again. So it's a tiny technical digression. So suppose C is a DG category, and like all our DG categories, it's co-complete with a T structure. And let A be an abelian category. And suppose you're given a functor from A to C heart. Then there are, under some technical conditions which are listed in the notes, then, so modulo conditions, this functor uniquely extends to a functor from what is called the derived category of A to C. So the thing is that if you have an abelian category, well, you all know that to an abelian category you can attach the triangulate category called the derived category. But in fact, you can do better. You can produce a very particular DG category out of an abelian category. Pardon?
Unbounded.
Yeah, it's co-complete, all kind of.
K-linear.
Yeah, sorry, we are K-linear. And so, and it has a universal property. It means that T abelian category, sorry, F is a T-exact functor. The T-exact functors out of your abelian category to the heart of a T structure in the DG category, unique, so such guys are in bijection with T-exact functors from the derived category to C. Not always, you need to put some conditions. And again, as I said this, what the conditions are in the notes. And so to accomplish this, you need a little lemma that says that if you consider this functor from D of rep G check heart, if you you can start with the triangulate category with the T structure. You can take its heart, and by the universal property, the derived category of the heart will map to the to your original DG category. It's not, of course, true that this functor will be an equivalence for any DG category with the T structure, but the claim is that for this particular one, it is an equivalence.
For which particular DG category do you take for D of A? It's a DG category.
Yes, there is a canonical construction of DG category attached to an abelian category. So explained very well in Lurie's book. Second Lurie's book, but chapter 1. Yeah.
What is your claim that these Satakis are equivalent?
Not at all. So this is an equivalence.
A theorem that you can have Satake naive.
So it's not a theorem. I'm saying that I can produce a functor in one direction, and it's called Sataki naive. Namely, I apply this universal property to A being rep G check heart. And because D of rep G check heart is rep G, this gives me the functor Sataki naive.
And G is reductive?
Yeah, well, because I'm using G in G check, I'm assuming that G is reductive.
What do you mean by the first factor?
Pardon me? Exact. Exact functor between abelian categories. All right, so.
In a Hadro spherical, right, a spherical category of a jet supporting finite dimension.
Pardon me?
In a Hadro spherical category.
Yes.
I mean, the object is supported on finite dimension.
No, I can take infinite unions. That's fine. Representations also, I can take infinite dimensional representations, but in the heart.
So Sataki naive is something as taking Sataki restricting to the heart and then inducing?
You don't know what Satake is yet. We haven't talked about it. There is derived Satake, which will be in the tutorial. For the main part of this lecture, there will be. So the real Satake, it's not needed for geometric Langlands per se, and it will be tutorial stuff. So for now, we'll be only using Satake naive.
What is not derived Sataki is not needed?
It's not really needed. But we'll cover it.
So what is the definition of rep G check?
Rep G check? You tell me.
I mean, yeah. You can have a billion category and you can touch the G category.
Well, we talked about rep of anything, right? Quasi-co and B.
But it's not the same thing.
It's what?
So it's some dilemma. It's not.
It's not tautological. It's true for any finite dimensional group. There's something to prove.
And the functor in the lemma is the exact.
Pardon me?
The functor in the lemma is the exact.
Yeah. Well, you kind of know what both sides are. Again, I'm not saying anything fancy. All I'm saying is that the category representations of the group thought of quasi-co BG can be recovered from the heart. That's all I'm saying. All right. So one, just for, well, to motivate the discussion during the tutorial, so this functor, the Sataki naive, it's called naive because it's really not an equivalence of categories. It fails to be fully faithful. From rep G check to sv is not fully faithful. So here is, Sasha, we just talked about it we spent 5 minutes. It's quasi-co of BG check. It is the derived category of the abelian category. So let me explain why it's not. So I claim that this functor induces not an isomorphism on endomorphism of the unit object. So if you consider the unit object, which is the unit representation, so it goes to endomorphisms of, well, the delta function at the identity of the affine Grassmannian. So well, you have a reductive group, endomorphisms of the unit object is just the field. Whereas if you think of what's going on here, so again, our sp was this equivariant category. So this is an endomorphisms of the, well, if you wish, the constant sheaf in the following category. It's equivariant derived category on the point with respect to G of O. So this is the delta function object. It's supported on the origin, so of the affine Grassmannian. So I'm considering X in this equivariant derived category, and this is otherwise known as the cohomology of BG, BGO. So and it's not at all K. So that's the failure. So you need to somehow, if you want to correct it, you need to correct the left-hand side to have all these X. So that's why it's called Sataki naive. All right, so that was our story over the point. I'm going to replace the check, but add the tutorial. So now we're going, so that's the beginning. Now we're going to generalize it in many different directions. So the directions that I want to take in this lecture, I want to replace, instead of having one point, I want to have multiple points. All right. So now I'll do, okay, so I now need to make a technical digression. Basically repeat what Sam already explained. So it's about this jet construction. We need some, well, we'll need it several times more in the future. All right, so it's not an equivalence. It's a functor in one direction.
Oh, okay, because of the problem.
Yeah.
Functor on factorization.
Yeah. So but before I do this, I have to extend both sides to factorization categories. So I want to do it in some organized manner. All right.
On the left, we do have one construction, but you want some.
Yeah. So I want to review both constructions systematically, and because we'll need them multiple times. Okay, so let me just review what Sam has already explained. So there's two paradigms for jets. There's kind of jets and horizontal jets. So we'll do both separately. First, we start with the following. Say you start with a z, which just lives over x. And to it, I'll attach 3 different factorization categories. I'll call them jets of z. It will be jets prime of z, and those will be very close. Sometimes they'll be isomorphic, and then will be jets meromorphic. And so it will be the first time that we'll be exposed to the ugliness of the formal punctured disk. We haven't encountered this guy yet, but now time has come. And that he is not a nice guy. Okay, I want to define this factorization prestacks. So, i.e., for every finite set I have to define the corresponding prestacks over x to the I derived. So,
what's the assumption on z?
None. So given a point, an S point of xi derived, about which I think has a map from S reduced to xi, I have to specify what does it mean to lift it to a point of this, this, and this respectively. All of these guys live over x to the I derived. So this is the easiest to say. So let me say what it is. So a lift to a point of jets zi is, well, remember the formal disk. Let me call this point xi. I'll remind you what this guy is. Well, let me remind you right away. This is, you take the graph of xi. So graph of xi is a union of graphs of, so xi is kind of I points of x. We call it xi. Take the union, set theoretically, and takes and complete. So you're completing x times x along the graph. So this is our, and it's a formal scheme. Okay, so we'll be using it all the time. So, pardon? X to the I. Thank you.
When you're talking about formal scheme, you mean that it's an in scheme?
It's an in scheme, yes. And Sam described for us the function.
No, that's right. It's the union of the graphs. It's union of Kac.
Oh, yeah, sorry.
On the first row,
Yeah.
x to xi.
X to xi derived is the same as the map from S reduced.
No, it's okay. I thought it was s.
Yeah. Okay. So I have this formal. So I have this formal. So scheme, and a datum of the lift to a point of these jets is just you lift it. So you map this formal disk to Z. So that's what it takes to specify a point of jets. Okay. Now I'll modify, instead of jets, let me say what it takes to map to jets prime. It will be a slight difference. Instead of this formal disk, I'll just erase the hat. So Sam, did you introduce the guy without the hat? Where's Sam? No. Okay. So what does it mean to erase the hat? Well, it means the following. Let me just first explain on an example. So let's consider it as the case of one point. So there is this. This is what's called spf k of t. So it's an in scheme, which is the colimit over I of spectra k of t in scheme. Now, without the hat, it is spec of this. So here we have to come to grips with this difference between spec and spif. So this is the formal scheme, that's an actual scheme. So what's the deal here? So what's the definition of this starting from this? So it's scheme, which is, it's actually a scheme which is affine over X, defined by the following universal property, that hom from d xi to any y is by definition hom, so affine X affine schemes. Hom over X is hom also over X, i.e., so you have this colimit, and you take this colimit in the category of affine schemes. And on the level of rings, you're taking the inverse limit of the corresponding rings. So this is, it's actually, so that was an in scheme, this is a scheme. Is that kind of clear?
The difference is that you take the limit in two different categories.
In one case, don't take the limit. It's one, it's a pre-stack. In the other case, I do take the limit inside affine schemes. Yeah.
For example, when you define this d hat,
Yeah.
should the s was reduced
Where?
the main line when it has
Here?
d hat xi is
This is S.
this is
So you see,
what do you mean by the graph of xi?
see, graph is, it's graph is a closed subset. I don't.
I don't know in what sense.
So I said what it is. It's a union. So what's xi? It's I maps.
Yeah.
Take the graph of each
Yeah.
and take their union. And I don't care what the scheme theoretic structure you put on the union, because you'll take the formal completion.
Oh, I see.
So on the left board, when you write S times X at the formal neighborhood, you mean the limit of the finite nilpotent in stacks and not in schemes.
Exactly. And D without the hat is affine schemes. Again, relatively affine to X. Okay, so this is D, and this is Jets prime. So note that kind of by definition, all of them are pre-stacks.
This branch is somehow much more intense.
So this xi have a map of pre-stacks, and therefore you have the restriction map. So you have Jets prime of Z restricts to Jets of Z. Now, tautologically, if Z is affine over S over X, then this map is an isomorphism. So if you're mapping to something affine, by the definition of my, well, this colimit, it doesn't matter if you're taking maps from D or D hat, it's the same thing. But, and in all the examples that we'll consider, there will be no difference between Jets and Jets prime. So in kind of most cases of interest, they yield the same result. We'll need the other one for the following reason. Now I want to do meromorphic. Look at the definition. By definition, when you're mapping to something affine, the two give the same result. That's the definition of D without the hat. So it's two D's, one with a hat, without another without.
I, lowercase I, and uppercase I.
There's no uppercase I.
There is on the right side. No. D without the hat sub X, and you wrote uppercase I.
It's gravitational, whatever you call it.
So there's a prime. There's a prime.
There's no prime.
No,
Oh, there's a prime. There's a oh, you wanted the primes? Or the xi's? All good?
meant the subscripts to be the same.
All good.
What's if Z is what?
Affine over X. Okay, now we're coming to the formal disk. So
So the jet is internal home in the category of stacks. I mean the category of stacks over X.
if you wish. Yeah. Okay. So now I want to define jets meromorphic. It will be the same thing, but instead of the disk, I'll have the puncture disk. Now, who is this guy? And so the reason that we talked about D without the hat is because we wanted to introduce this guy. So remember, this was a scheme. Sasha, if you have a question, you can ask me. So then don't ask. So we define this as a scheme, and it contains the same old graph as a closed subset. So this old graph whose formal completion along which we took to produce D with a hat, by definition, it sits inside the scheme as a closed subset. Now, because it's a closed subset in a scheme, you can take it out and obtain an open subscheme. And this is the puncture disk. So the problem is that we could not have produced a puncture disk while staying in formal geometry. If you took your closed subset out of that in scheme, you'll be left with the empty set. It's the that's why we had to deal with this guy, and this guy is not nice because it's not a finite type. So pardon? Yeah. Yeah. So, and here comes my ignorance. So, like, if I knew rigid geometry, I would maybe be in better shape. Okay. Okay. So this is the formal puncture disk, and now you map. It's a scheme. You're mapping out of the scheme, and you get meromorphic jets. Okay. So these are the three incarnations of jets. Now I'll do one more in a different context, but only the simple one. And this is this one that has been explicitly done by Sam. So now I'll start with a different kind of datum. I'll start with y that lives over not x, but x deram. And I'll produce another factorization space. I'll call it jets horizontal of y. So again, I have to say who it is. So I need to define jets horizontal y I as living over xi deram. So I start with the same kind of datum. I start with a map S and S reduced, call it xi to xi. And I have to say what kind of data is it to lift this to a point of this. So here's the definition. Again, I'm just repeating what Sam said. So a lift of xi to a point of jets horizontal y is the following map. So you take your nice disk, but you take its deram space and you map it to y over x deram. So you should think. So let me do the case of one point. So in this case, I take the spiff let me just make it more interesting. So I'll write this thing. So what will be spiff of this times s. And I'm mapping it to y. But now I'm taking a spiff of this deram. So my question is, what is spiff of this deram? What is it? Is what? It's 1 point, indeed. So it kind of does nothing.
Isn't that true in the general case? You should just remove the form of completion.
Well, if your points are disjoint, so the fiber of this over disjoint points is just the product of fibers of the original y. And nothing happened. What this definition does, it tells you how to collide. Again, the space fibers over x to the I derived over disjoint locus is just, well, y, but then something happens, and along the diagonal it's one copy of y. It's just kind of a algebra geometric way to say how to glue them together.
Sorry?
Yes?
Can you say why this point? Or why is it?
So, see, when I take Theorem, you lose completely the information about nilpotents.
I have a question, suppose that. So Sam yesterday explained somehow if you have an algebra with connection, he sort of on the long functions he kind of explained how to produce factorization algebra. So
It's that.
So is it
It's this.
obvious that this is the same?
It's absolutely obvious.
Is it the exercise that Sam put?
No. The brutal exercise was something completely different. It was some exercise in combinatorics.
Cruel exercise.
The cruel exercise.
But why isn't this the solution to the cruel exercise?
No, because he, in his own talk at the end, he gave the solution. He said that instead of doing the cruel exercise, I'll give you the algorithm. And the algorithm he gave was this one. So the cruel exercise had to do with the end of his second lecture today. So when he produced out of commutative symmetric monoidal category, he produced a factorizable category. And so on the second power of the curve, he wrote an explicit formula. The cruel exercise was to write the explicit formula for any power of the curve. So it did some combinatorics.
But this kind of replaces it.
So this replaces it. So this replaces for algebras. For categories, you can't do such thing. So for categories, you still have to do the cruel exercise. So again, it's cruel only in combinatorics. You have to write down some limit and colimit, some blah 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 thing that will tell you what is the factorization algebra course on ith power of the curve. All right. So now let me introduce the actors. All right. So G of O, it's a factorization group scheme, which is by definition our jets into G.
Did you define just horizontal, or are you defining it now?
There.
How does G map to X around?
Pardon me? Okay. Also isomorphic to jets prime. No, it's jets, not horizontal. Jets for things over X itself. Okay. G of K, it's factorization group in scheme, and that is jets meromorphic of the same thing. Yeah, I should have said that. I forgot to mention. Sorry, that. So we have this D hat maps to D, and that also receives a map from this puncture disk. So therefore, we have jets prime mapping to jets and mapping to meromorphic jets. So basically, if you want to connect jets to meromorphic jets, you need to go through this gadget. That's why we introduced. I mentioned it. Okay, so these are the two gadgets that we'll be dealing with. And so why did I mention? Yes?
Why isn't it an extra run?
So we introduced this notation, jets, for z over x, and jets horizontal for y over x derived. So, but you could have asked a different question. Why did I stop here? I defined jets, just jets horizontal. What about jets prime horizontal? What about jets meromorphic horizontal? What about that? Any ideas?
Can you have meromorphic horizontal? Become polymorphic?
So,
Somehow the crucial property of jets horizontals explains that when the points are distinct, it's just product of the
yeah.
original y. So somehow, from this point of view, I really don't understand what you should want from the.
Indeed. So, unfortunately, we can delay this question for 2 days. So the claim is that there exist also jets prime horizontal, jets meromorphic horizontal. They're more complicated to define, and I'll explain in a second.
But can you say what happens
I'll
just over the curve itself?
I'll give an example in a moment.
So, but G of K is for G times X, not for G times X derived?
Again, jets without horizontal was defined for z over x.
The one below.
Yeah, exactly. Jets and jets meromorphic without the subscript horizontal was defined for z over x.
Sorry, that's meromorphic, not horizontal.
Meromorphic, sorry. Horizontal with a subscript. Okay.
Can you obtain one from the other by some taking horizontal sections C2L or something?
You mean horizontal versus not horizontal?
Jets horizontal from jets.
You can go the other way. You can get jets from jet horizontal. So namely, if you have any z over x, you can do restriction of scalars a la v of z, and it will be over x derived. So jets horizontal into this is the same as jets into this. Again, so there is a procedure called restriction of scalars a la v. There was this guy. And by definition, okay, we don't need this. So I'm saying that the jets is a particular case of jets horizontal.
It's true that if you consider jets horizontal over x itself, you recover the original y.
Okay, let me not address this question because I don't want to. I didn't understand what you're asking. I know, and I don't want to. Because. Okay, Sasha, I'll say something much more interesting right now. Okay, now take y to be bg times x derived. And so consider jets horizontal into there. So this is the guy that appears in Sam's talk, and we have another name for it. This is so we define the factorization space of local systems on the non-punctured disk to be jets horizontal into this gadget.
Why?
You'll see in a moment. Well, notation, x derived.
So you consider bg cross x
as something over x derived.
as something over x derived over x derived.
And then I take jets horizontal into there, and I define this. Now let's see what it looks like according to Sasha's analysis. So again, it's a factorization something. What is its fiber over n distinct points? Well, according to what Sasha said, you just take the original thing and take its fiber over n points. Well, our thing was constant, so what I want to say is that if you take log cis and consider it's over a distinct collection of points of your curve, all you'll see is bg taken n times. And that's kind of
Comment on this. So log 6g of d check. What does it mean?
d puncture. It's not the not non-punctured disk d hat.
But I don't know so it's local systems on the form
on the formal disk.
But which you make into.
A factorization pre-stack.
Did you explain how to make this?
Yes, just horizontal.
Oh, you're saying that this, but you're saying that's, you're just explaining that if you take just horizontal fiber, you want to explain now that it's fiber over one point is exactly sort of naively that's local.
Yes, it's exactly, so let's see what it is. It's BG taken n times, but that's exactly what you expect, because you expect local system of the non-punctured disk to be just BG. Yeah?
In the RAM set.
DRAM, nothing else exists for now. Okay, so this is the factorization space which is log-sys. So let's just, well, to give you a preview, when we will define jets horizontal meromorphic, this will give us, it's a tricky construction, but once we do this, we'll get the notion of, well, this factorization pre-stack of local system on the formal puncture disk. So, all right. Okay, Sash, you're kind of, if you want to ask the question, ask the question.
I'm trying to say something really stupid. I'm trying to
yes.
say why local systems on the check is the same as BG.
What, on what? On the formal disk?
Yes.
So what do you think of formal local system on the formal disk are?
So just take space of one quotient by the.
Well, and then you can easily see that any one is gauge equivalent to the constant.
No, that I know, but somehow, but also you have something to stabilize.
And the stabilizer is G. Automorphism of the trivial local system.
Isn't there S on the...
Pardon? No, I just computed the fiber. So if you have S, it'll be just G bundles on S. So like a long S, you don't have a connection. All right. So now we are in the position to say what is Sf I. So this is D modules. Well, and again, in the next hour, I'll set up this theory so that it makes sense. And so this is a factorization category, and you can consider Giron. And moreover, but it's not just a factorization category, it has an additional structure. So note. Pardon me?
K, I, and O is just i's power.
Yes, that's my notation for the value of this thing over x to the I. In the notes, I use this notation. It's just notation. So one important piece of information is that these guys are not, it's not just a factorization category, it's a factorization monoidal category. So that kind of, it's monoidal relative to the Ron space. And the monoidal operation is given by the same formula as before. And so this is what we get using these guys. And we also get this category rep G check I, well, it is quasi-coherent sheaves on log-sys. So if you use this factorization pre-stack, and if you take local quasi-coherent sheaves on that, that's our definition, just according to Sam, of what, well, the factorization category that corresponds to representations of the group. All right, so I think that was my hour in which I didn't do anything of what I was intending to. So let's have a break, and then we'll continue in the framework of tutorial.